right. Thank you, everyone, for joining me. Sorry about that, a little bit of technical difficulties. Today I'm going to present on the twin tub girder bridges in Texas. And so hopefully you'll walk away with a little bit more knowledge about twin tub girders and maybe steel bridges in general. And so first I want to ask if you could just by raising your hand, just so I can kind of know the audience, who has experience with bridges and just bridges in general, whether it's a design or construction, maybe a class that you took in college. Okay, great. See a lot of hands going up. Great, thank you. Well, if you don't have experience with bridges, that's okay too. So today I'm going to talk about a little bit of the background for this topic. We're going to discuss research that went into the twin tub girders, and then designing for redundancy, the SRM methodology. And so tune in if you don't know what SRM is, because we'll talk about that. We're going to talk a little bit about FHWA approval moving forward. And then if you stick around, we're going to have some exciting bonus material. So please stay tuned. So moving on to background. So if a bridge has a tension element that if failed would cause a total or partial collapse of a bridge, it's classified as fracture critical. And all two girder bridges are classified as fracture critical. So I do want to point out that just because a bridge contains members that are classified as fracture critical, it doesn't mean that there's anything wrong with a bridge or that the bridge is unsafe. It just means that there's a higher quality of standard for the fabrication of those elements. And then it's going to also require more in-depth inspection than other steel bridges. So it doesn't mean that anything's wrong with it or it's unsafe. It's just a term. So in the same topic of fracture critical, we also need to talk about redundancy. And it's crucial to identify the type of redundancy that's present in a bridge. It allows the load that was previously carried by a failed member to be redistributed to those other members so that you can avoid collapse. And it can be provided in one or more of the following ways. So you can have load path redundancy, structural redundancy, or internal member redundancy. So the first one, load path redundancy, it's based on the number of main supporting members between the points of support. So bridges with 3 or more main load carrying members or load paths are considered load path redundant. If one bridge were to fail, or if one member were to fail, the load has a better chance of being safely redistributed to the other members. So an example would be like a bridge on the right that has, it's a multi-girder bridge. And so historically, for the purpose of identifying FCMs, redundancy has been defined primarily based on consideration of load path redundancy alone. So the next one, structural redundancy, is provided by continuity in the main members over interior supports. So as you can see in this picture, there aren't any joints at the supports. The member is continuous over the supports. So in the event of a member failure, the loading from that span can be redistributed to the adjacent spans. And so the bridge failure may not occur. And the last one, internal redundancy, it's if a member contains 3 or more elements that are fastened together so that the multiple independent load paths are formed. And so the picture on the right is a great example. This is taken in Llano, Texas, from the Llano River Bridge, and this is one of the gusset plates. And so as you can see, there's a lot of built up members going into this joint. So now let's talk about twin tub girders. They consist of 2 steel box girders that are composite with the deck. And so as you can see in this picture, this is a transverse section. So we took a cross section out of a span of a bridge. You have your 2 box girders, and then you have shear studs that act compositely with the concrete deck. So these types of bridges are very effective for curved ramps and connectors in multi-level interchanges. This bridge is in Austin, Texas, at I-35 and US 290. So as you can see, they're very good for curved bridges. So for these types of structures, the bottom flanges and the webs are considered fracture critical in the positive moment region. And so if it's been a while since you've taken a structural analysis class, and you're kind of unsure about where this would be, I've kind of sketched a moment diagram on this bridge. And this is the way I learned. So I know some people, they flip it opposite, but so just for this talk, I've sketched the moment diagram. And so the positive moment would be in these areas that I've indicated. And as you can see, the tension is going to be on the bottom. So that's going to be the fracture critical member. And that's going to require the special fabrication requirements, as well as the more frequent inspections. And so, like I said, it has special inspection requirements, and that's a hands-on inspection. These are required every 2 years, and they often take place at night. And this is just because of the high volume that's usually on these bridges, and it can also require very costly traffic control. So as you can see in this picture, this is at night. They've got a snooper out where they're going to be inspecting this bridge. And it can also be unsafe. It can be unsafe for the traveling public as well as the inspectors because you've got different traffic patterns. So there are various types of fracture critical members on bridges. The twin tub girders happens to be one of the most common types in Texas. We have over 480 existing twin tub girder spans. We spend roughly about $2.3 million every 2 years on inspection. And you kind of see in gray there, this doesn't include traffic control. And so the cost definitely goes up, and the traffic control cost varies depending, of course, the number of lanes closed, the complexity of where exactly they need to close the lanes. And so it's very expensive. So next I want to talk a little bit about research. In 2010, TxDOT completed the modeling and response of fracture critical steel box girder bridges research. It was conducted at the University of Texas at Austin, and it's project 5498. So if you hear me say 5498, that's what I'm talking about. I'm talking about this research. It characterized the redundancy that exists in twin tub girder bridges, and it included a combination of lab testing, full-scale testing, and detailed structural analysis. So on the right, you see a picture of the bridge that they tested, and this is an actual structure that was taken out of service from Houston, and it was hauled to the Ferguson Laboratory in Austin. So this was an actual bridge, and they reconstructed the deck and the rail on this bridge. It was simply supported. There were no external intermediate diaphragms, which those are the members that connect the two girders together. The bridge rails had expansion joints, and it was horizontally curved. So this pretty much represented the worst case scenario. So I want to get a little bit into the actual testing because I think that's the exciting part. That's where we can blow things up, right? So the first test, they had a linear shape charge, and they rapidly cut that bottom flange at the most severe location. They put an HS truck load above the fracture, and the bridge only deflected 1 inch. So the bridge performed very well. So for the second test, the bridge was raised back up to its original elevation before that first test using scissor jacks. The web was then cut on the same outside girder that the flange was cut to provide a full depth fracture. The loads were induced and applied suddenly by an explosive acting on a temporary support system. And the bridge performed very well again. The fractured girder only deflected 7 inches. And so, as you can see, even in its damaged state, the bridge could support traffic and did not collapse. And then lastly, the third test, as you can see that test, this is where we want to break the bridge. They incrementally loaded it, which means they just over time added load, added load, added load. This occurred over a very long period of time. And it was almost comical. We have reports coming back to Bridge Division, oh, the bridge is still standing. It still hasn't failed. And then finally it did. It was able to carry 363,000 pounds. So wow, that's more than 4 times the legal truckload. So it's a pretty strong bridge. So this clearly demonstrated, the redundancy for this span that, as you remember, was not designed to have system redundancy. So this bridge was just taken out of service. There was nothing special. There was no special consideration for redundancy. And it highlighted the importance, some of the things that came out of the research was that the deck and the shear connectors definitely contributed to the system performance. And then also the barrier railing contributed structurally. So next I want to talk a little bit about designing for redundancy. So 2010, the research was completed. In 2012, a memo came out by the Federal Highway Administration, and that was a clarification of requirements for fracture critical members. And it introduced a new member classification, a system redundant member, which is SRM. And that member, if you were to classify that, it still requires the fabrication, the special fabrication like the fracture critical member, but it doesn't have to be considered for that hands-on inspection. And then also the memo goes on to state that that SRM designation should be shown on the plans. So this provided a path to design new steel girder spans that could shown to possess adequate redundancy so that the bridge wouldn't collapse and safely support live load. Because that's what you want. You want the progressive collapse mentality. You want it to still be able to stand up and support live load. So this got TxDOT to thinking, what if we could design new twin tub girder bridges to be system redundant? And that would eliminate the requirement for that expensive hands-on inspection every 2 years for the life of the structure. So now what? We have the research, we have the memo, what are we going to do? And so after that memo, TxDOT met with FHWA, so Federal Highway Administration, to discuss a path forward. And they decided that the best way to move forward was to, do a little bit of research on our own existing structures. And so we had some redundancy case studies. That 5498 research developed a simple method where they assume a simulated full depth fracture in one of the girders. And so TxDOT bridge engineers analyzed 3 existing steel twin tub girder bridges, and they used that simplified modeling procedure to analyze it. So I'm just going to go over the 3 bridges. The first one was in Austin on US 290. It was a 1998 design, and the total length of the unit was 603 feet. And it was 3 spans, and it had a radius of 716 feet. The next one was in Waco that they looked at. It was at IH35 and SH6 direct connector. It was a 2007 design, around the same length as the first one, and the radius was greater at 1,033. And then the last one they looked at was in Dallas on Interstate 30. It was a 2008 design. It was a 2-span unit, so this one was a little bit different, and the centerline radius was 895 feet. So the results of the redundancy case study They indicated that the intact girders had sufficient bending capacity, as well as adequate deck shear strength and shear stud tensile capacity. In all cases, the intact girder failed in combined torsion and shear at the supports, but the margin of inadequacy was small. And so another thing I kind of want to bring up is that compared to that 5498 research for that experimental bridge, the three TxDOT case studies had longer span lengths. The experimental bridge span length was 120 feet. The case studies also had a sharper horizontal curvature, which that leads to a greater dead load, larger eccentricity, and higher torsion and shear at the supports. And so all three cases didn't pass the simplified method at that support girder section shear capacity check, and that was due to the large torque and shear forces. So none of the cases failed due to the lack of the shear stud tensile capacity. So this led TxDOT to believe that new steel twin tub girder bridges could be designed and detailed for system redundancy. And so that would be, that was a great solution, moving forward, is to design them for system redundancy. So I have one more question. Who here on the call knows what the Texas Steel Quality Council is? If you could just use the raise hand button at the bottom. That'll also give me a chance to get a drink of water. All right, thank you guys, I appreciate it. So it looks like we have a couple of folks that know what this is. So the Texas Steel Quality Council is a joint owner industry forum. It's been around since actually 1995. It was started at TxDOT, and it's a forum of TxDOT engineers and people that work in materials and fabrication, TxDOT inspectors. We also have consultants that come, FHWA, academia. We have fabricators, detailers, steel mill reps. So it's a great organization. We meet once a year, and we actually just met in the spring, and we're going to have another meeting in September. So if you're interested, let me know. And we're going to try to get back on the schedule. Normally they're in the fall, but we kind of missed last year. And so that's why we had a spring meeting, and we're going to have another meeting in the fall. And we always have a great agenda, very informative. And we talk about things that are going on in the steel world, steel bridge world, as well as solutions. And we also have a lot of great presentations. And so the reason why I'm telling you about this, because in 2016, we formed a twin tub task group. We called it T3. No, just kidding. No, it was twin tub task group. And the members of this task group reflected the structure of the Texas Steel Quality Council. And the goal of this task group was to develop design specifications for engineers to use to design for redundancy for steel twin tub girders. And this was just, this was so that the goal would be that we would have non-fracture critical steel twin tubs out there. Again, so we wouldn't have to do the inspection, the very in-depth inspection, right? We're still going to go out there and inspect the bridge every 2 years, just like every other bridge in Texas. We get eyes on it every 2 years with a routine inspection. And then in the off years, we go in with a maintenance inspection. And the maintenance section of TxDOT looks at the bridges. And so every year a bridge gets eyes on it. So through that group, an AASHTO ballot item was developed, and it was presented at several industry and AASHTO meetings. And I say several, I can't even remember how many times that we presented. It was a lot, just to kind of get the word out. In the end, unfortunately, AASHTO didn't approve our ballot item. So definitely disappointing. But the good news is that we were encouraged by FHWA to submit approval for our own state, because it wasn't that AASHTO didn't like the ballot item, it was that they just weren't ready for language in the specification that was specific to twin tubs. And there was also some other research going on too. And so they kind of wanted to wait, I guess, to see that out. And so what we did is we developed our own language for the Texas Bridge Design Manual. So that kind of leads me into talking about our design methodology. So right now we have a design methodology in the Text.Bridge Design Manual. And if you've never opened this, you just Google Text.Bridge Design Manual or use the search engine of your choice. And you should, it should get you there. And so in this manual, you'll find a section on twin tub girders and designing for redundancy. So I do want to note too that this moving forward, this is kind of monumental. All twin tub girders, they must satisfy the requirements of this manual, and so they must be evaluated for system redundancy moving forward. So if you were to design a bridge, a twin tub bridge, you would first design it as you normally would, with the AASHTO specifications and with all of the publications out there to help you design this type of bridge. There's many, and we'll talk a little bit about that at the end. And then you would design the bridge for member failure. And of course, that's a simulated member failure, right? And so basically you would, sever the bridge at a location, a chosen location. And we tell you how to do that, and I'll talk about that in a minute. But within this policy, we also introduce an extreme event load case. So we introduce a new load combination, which is extreme event 3. And we basically revise the extreme event limit state to include a structural member or component failure. And at the middle of the screen, you can kind of see the load combination and the load factors for that. And they're also, if you see on the left, they're all multiplied by 1.2 factor, and that's an amplification factor to simulate the dynamic effects of a fracture, because if a fracture happens, it's sudden and it creates energy or a dynamic effect. So we have to count for that. And so as far as, now I kind of want to talk about, which girder would you simulate the fracture and where would you fracture the girder? And so we have all of that in our specifications in the Text.Bridge Design Manual. So basically you would fracture the bottom flange, and so what I have there in blue is the bottom flange and the webs that are attached to that flange. And you would assume that those would be fully fractured, and you would determine the location within that span using a strength 1 load combination. So you would use the maximum factor tensile stress and it's basically it's most likely going to be at the middle of the span. So you would also we want to take the worst case loading scenario, and so you would choose this based on the cross section and relative to where the traffic lanes and the eccentricity to the deck and the railing. Also, the criteria points the designer to check simple spans or the ends of spans continuous unit, and that's because we're already telling you that's going to be the worst case. So you don't have to try to figure that out. Your worst case is going to be your simple span. So that's what you need to check, and that's what you need to assume. If the span is horizontally curved, it's going to be the girder with the largest radius. That's the one that you're going to assume to be the fractured girder. So if you look in this plan view of a twin tub girder bridge, it's going to be that outside girder because it has the largest radius. So the manual also has live loading criteria. And so it's going to include both truck and truck and lane load information. And then it's also going to talk about where the truck is positioned, which you're going to want to put it at the worst case, which is right above the fracture. And then also there's information about the number of design lanes. And those are going to be the number of actual stripe lanes. They're not going to be, if you design bridges, it's not going to be, like you would for your other load combinations. And next, I want to talk a little bit about internal and external diaphragms. So this picture shows a framing plan of a twin tub girder bridge. And if you can see, I've kind of highlighted in blue the center lines of each of the twin tub girders. And so basically, if you're not familiar with bridges, the framing plan is basically a plan view of the bridge. And it's going to show that center line of each twin tub in relation to the diaphragms, the bent lines, the profile grade line. You're going to also see locations of field splices. So it's basically showing you a layout of the bridge. I just also want to highlight that these are the external intermediate diaphragms, because a lot of people may not be familiar with those. And so those are the diaphragms that are going to connect the two twin tub girders. So if you're designing for that member failure, you want to make sure that you provide internal and external diaphragms at all the supports. And so as you see in that picture, this is typically already done even before this policy came out. You can see a diaphragm connecting the two girders at the support. And then also the internal diaphragms, and the external, they must be designed to resist that torsional moment. Like we talked about earlier, there were some issues with that on our existing bridge case studies. And so you definitely want to design for that. You need to design so that you can transmit those vertical and lateral forces to the bearings. So you need to get those loads out to the supports. And then also they need to be designed to act compositely with the slab and the shear connectors. And this is more of a detailing criteria. And so you're going to want to have at least two external diaphragms, those intermediate diaphragms, the ones that I highlighted in red on the layout. You're going to want to have those on each side of that location of the maximum factor tensile stress. And so, and you're going to want to have that on each side of that. And so this is kind of an extra just conservatism, and it's intended to enhance the system redundancy, and it provides additional load pass on each side of that assumed fracture location. And this is something I definitely want to highlight because typical Texas practice is after the bridge deck goes on, it's hardened, we remove those external diaphragms and for aesthetic reasons, because we don't need them after the deck is hardened. But with this new criteria, you're going to leave some of them in place, and they're going to be full depth diaphragms. So again, going back to structural analysis or just, your structural design, you're going to want to check your flexure and your shear for the portions of the intact girder that can still, and then also the fracture girder that can still resist that load. And then you're going to use AASHTO, and this is all in the manual. I'm not going to go too far into that just because I kind of want to touch on a lot of different aspects. You're going to check the shear for the top flange lateral bracing. And if you don't really know what that is, I'm showing a picture here on the right. And those are the top members that are diagonal on this picture. You also want to check for adequate shear resistance to resist that shear in the concrete deck due to the torsion after the fracture event. And then next you want to check the end diaphragms. So this is a picture on the right of an end diaphragm. And you want to check to make sure that the connection to both the tub girders, to make sure that they have adequate shear resistance after that assumed fracture event. And then very important, you want to check the shear stud connectors because those are what's going to connect the deck that's going to kind of transfer that load after that fracture event. And you want to make sure there's sufficient tension capacity and that they develop a plastic beam mechanism. And then another detailing, best practices, but it's also policy. You want that bottom mat, shear connector to extend above the bottom mat of steel, like I show in this picture. So another part of this, we know that as engineers, we know that the most accurate way to assess the redundancy of a complex system, like the twin tub girders, is through finite element modeling. But these models require a substantial amount of time to develop and analyze. And so a simplified method for evaluating the system redundancy for these twin tub girder bridges was developed. And it was based on the behavior that was seen in the 5498 research that we talked about. And so we allow, the TechStop method allows two different types of analysis, an approximate structural analysis and refined structural analysis. So the approximate structural analysis, it's basically after that assumed fracture event, the entire self-weight of that span and the entire live load is assumed to all go to the intact girder, and the fractured girder is not carrying anything. So there's also a little bit of criteria before you can use that approximate structural analysis. Your spans can't be more than 250 feet. You can't have a heavy skew or a very tight radius of curvature, so we have limits on that. And then of course, like, everything, you need to use your best engineering judgment. Here are some screenshots. We also developed a guide for this simplified method, and it's a step-by-step procedure that's outlined here, and this is in the TechStop Bridge Design Guide. So there's a manual and there's a guide, and kind of like what I've highlighted here, it goes step 1, step 2, and it takes you through the simplified method. You can create spreadsheets off this guide, and it's very simple to follow. Here are some more screenshots that I'm showing you. There's about 17 pages in all, so I'm not going to show all of that. But as you can see, it's just, gives you equations, graphics, just to kind of help you walk through the analysis for this. And then of course, there's the refined structural analysis. That's going to be your finite element model. So before, the simple analysis, we're taking all that load and we're dumping it into the intact girder. But we know just from the research and just, from the testing that that's not actually what happens, right? Even after that assumed fracture, that fractured girder is still going to be able to provide some structural resistance. It's still going to be able to carry some load. And so with the refined structural analysis, you're going to model that. You're going to model that load distributed between that intact girder and that fracture girder. And I'm not going to go through all this, but the refined analysis, those procedures are set up in that 5498 research. It's all in there. And like I said, this is not this is even as far as it goes to FEM models and analysis, you take it a step further. This is going to be a nonlinear FEM. And so if you know what that is, you know that that's very time consuming and in depth. So if you want more information, like I said, in chapter 3 of section 17, you're going to find everything you need as far as the policy. And then also in our design guide in chapter 3, section 12, is going to be more of the commentary. It's going to be kind of the whys and the background. It'll give you references if you'd like to go look at more reports through NCHRP. And then also there's that appendix C that I showed you those screenshots. That's going to give you the step-by-step procedure for the simplified method. And then also, if you Google or look in your search engine for the Modern Steel Construction October 2020 issue, there's also a write-up about this. And it's kind of takes you through a lot of what I presented and maybe a little bit more further in depth. And it's definitely out there if you guys, it's free if you want to look at it. And it was written by myself, Greg Turco, who's also TechStop Bridge Division, John Holt, who is currently a consultant, but he was formerly at TechStop Bridge Division, and then Dr. Carl Frank, who is a professor, or who was a professor at University of Texas, and he's now a consultant. These gentlemen, as well as Mike Grubb, helped tremendously in the very beginning stages with the AASHTO ballot item. They were the authors. They helped author that. Definitely want to give kudos to them because definitely appreciate everything that they do for the steel bridge engineering community. And so next, I want to talk a little bit about our approval process. So like we talked about before, that memo that FHWA came out with in June 2012, it allows us now to demonstrate that a structure has adequate redundancy. You couldn't do that before that. It was automatically fracture critical if it met the criteria for fracture critical. And then it had to have the special fabrication and it had to have the special inspection requirements. But so this was great, you know, that now we're able to classify members as system redundant. Under this memo now, owners such as TxDOT or other DOTs, we must submit each bridge to FHWA for approval. So as you know, TxDOT has a lot of bridges and we build a lot of bridges every year. And so our goal was to be automatically approved by FHWA if the bridge was designed using our SRM methodology that I just presented for the twin tub girder bridges. So in May 2018, we submitted our design manual language for that method to FHWA. And so the process is that we submit to our Texas Bridge regional person, and then he submits it to FHWA headquarters, which is in Washington, DC. They discussed our methodology, they sent questions and comments back to us, and you know, we would respond, and then it would generate more questions just to make you know, things more clear. This was a great process, I have to say, and you know, definitely it lasted a while, but it made our language and the manual more clear, the questions, because we knew that if they had questions, others would have questions. Also, another great thing that came out of this process was our Appendix C guide for the simplified method. That was created so that it would help explain to FHWA what we were trying to do. And so this process occurred over several iterations. And in December 2019, we were able to party. I'm just kidding. We were able to celebrate that we received approval for our SRM method. So everyone was extremely happy that this went through, especially all the people that were involved. So next, moving forward. So moving forward, we're going to design all twin tub girder bridges using that TxDOT methodology so that we can classify them as a system redundant member. And we're still going to fabricate them with the upgraded quality as far as fabrication, like we would with the FCMs. We're just not going to have to inspect them with that you know, the special hands-on inspection every 2 years. And like I said before, there's still, every 2 years, we're still going to do a routine inspection, just like we do on every bridge in Texas, over 54,000 bridges in Texas. And then every off year, we're going to do a maintenance inspection just to get eyes on the bridge. Texas is we're currently developing spreadsheet tools just for in-house use right now. So that we can use for the simple analysis application. We're also developing refined models. And then this is mainly to provide guidance for people, for engineers, for when they're doing their redundancy evaluations, if they choose to do a refined model. And we're also looking at our existing bridges out there. Like I said, you know, there's 480 existing twin tub spans and counting, right? And so we're looking at those. We've located those and we've created a spreadsheet with all the different geometry information and the different criteria that these existing bridges possess. And then we're also kind of switching gears and looking at other types of fracture critical components for bridges, and that's the steel box straddle cap. So we have a research project right now at the University of Texas at Austin for this, so that we can you know, have some redundancy for these type of structures, because these are another type that we have to go in every 2 years and do that hands-on inspection. All right, and so I just want to thank everybody for sticking with me. I know how it is on webinars now. There's so many of them. because of the pandemic. So I appreciate you guys sticking with me. And like I promised, I have some bonus material for you guys. So stay tuned. So now I have another question. If you could use that feature again at the bottom, that raise hand feature, who has designed a steel bridge in the audience? And please let me know. Okay, thank you guys, appreciate that. So I want to talk a little bit about steel bridge design resources. So even if you haven't designed a steel bridge, you may in your future, or if you're not a bridge designer, you probably know somebody, right? And so that's what ASCE is all about, networking and knowing different disciplines of the civil engineering. Or that's one of the things that's great about ASCE. And so I want to share with you some resources. I think they're wonderful. If you don't know them, hopefully you'll remember them. And the first one is the preferred practices for steel bridge design. This document should be opened if you are designing a bridge in Texas. Well, you know, when I design bridges or steel bridges, even if, you know, I've already looked at this document, every time I would re-look at it, reread it. It's got great information. And, you know, especially if you're used to designing bridges from out of state, it's going to be different in Texas. We've done a lot of research. We have a lot of things in practice that you know, just know best practices. And so this document is going to help you. There's many things in the document. You know, there's preliminary design recommendations, span configuration. It's going to give you kind of some recommended practices to kind of staying within certain span configurations, girder spacing, flange thicknesses, web depth thicknesses, bearings, hauling. You know, it's great to design these bridges, but are you going to be able to haul that girder to the job site? And so it gives recommendations on maximum height and field lengths, as well as girder sweep. We have steel bridge standards. We have the SGEB, which is going to have all of your elastomeric bearing details. We also have an SGMD, which is the miscellaneous details, and that's going to be, you know, numerous things. You're going to have bearing stiffeners, skewed end details, cross frame and diaphragm details. There's the miscellaneous slab details. This is another great one. So definitely take a look at all of these if you're designing steel bridges. The SGS TS, which is a thickened end slab standard. And then next, there's some national resources out there, and that's the National Steel Bridge Alliance, which is NSBA, and particularly this AASHTO NSBA collaboration. And this is a group that's been getting together for a long time. I don't know exactly when it was instituted, probably in the early 2000s. And I'm sure that information is on this website. But this group meets every 2 years, and they talk about the various different topics of the steel bridge industry, and it pertains to design, fabrication, coatings, anything you can think of that goes into steel bridges. It has, this collaboration meets and they create these documents. They have the, you know, design details, guidelines, bearing design, steel girder bridge analysis. They're all free and they're all on their website. The one I have a picture of is probably one of my favorite ones. It's the Design for Constructability and Fabrication. And TxDOT, we actually have somebody that sits on these different committees. And I used to, years ago, be involved heavily, not as much anymore, but I try to as much as I can. But I definitely recommend you guys take a look at these if you're designing steel bridges or you know somebody, please let them know. Next, there's a guide to navigating routine steel bridge design. So this is going to be, if you're, you don't have anything more really complex, this is going to be a routine steel eye girder bridge. This is going to basically walk you through a path on designing this so that it takes you less time to design it. This has just came out, so it's brand new. It just came out in April. They've done a lot of work on this, and it's a great product. I definitely recommend. Next, these are some other things that you can find on their website. I want to point out at the top right, that Steel Bridge Design Handbook. This is a great handbook. There's 19 volumes. There's examples. There's design examples for 3-span, 2-span bridges. There's even a tub girder design, and it's reviewed heavily by all the DOTs. So it's definitely worth looking into. And if you scroll towards the bottom of the same screen, you're going to see the steel span to weight curves. And I wanted to point this out. And honestly, I wanted to talk about these resources because, Bridge Division, we look at a lot of plans from consultants, and, we're running into some things lately that we haven't seen in the past. And so, all these resources are out there for you. And the steel span to weight curve is huge. So if you're designing a bridge, go look at this, because it's going to tell you, hey, am I way out of the ballpark? Am I way over designing this? Is it too light? I mean, am I going to have some stability issues during construction? So look at these items. It'll help you in the long run. And so that is all that I have today. I just want to say thank you for letting me speak. And I hope that it was informative and that you got something out of it.
Well, Jamie, thank you. We have a question. It says, if twin tub girders are designed per new TxDOT guidelines, do the members still need to be fabricated to meet FCM steel fabrication requirements?
So yes, that is correct. And it is in the manual that you do need to still, the members still need to be fabricated per AWS, and that's the Fracture Control Plan. I believe it's clause 12. And so that's just going to give you a higher quality fabrication for those SRM members.
All right, and another question, and if you do have a question, please go to the Q&A in the control panel and type your question in. Who does the bridge inspection? Is it TxDOT or consultants or a combination? And how does a firm get qualified to do it?
So the inspections are done by TxDOT and consultants. Because we have so many bridges, yeah, there's just not a way that TxDOT could do it on our own. And then I think the second part of the question was getting training. And so to inspect bridges, you have to be certified, and you have to take a class through, I believe it's, the name is escaping me. It's NHI, but I can get that information to you. But yes, you have to take a class. And if you're not an engineer, the class is 2 weeks. But if you are an engineer, it's a week, because that first week for non-engineers, they go over a lot of the engineering principles. And so it's definitely a good class, even if you're not going to be an inspector. I was never a bridge inspector, I was a designer. And I recently took that class about a year ago, and I wish I would have taken it sooner because it's very good. It goes through all the different elements. I got a lot out of it.
We've got another question. What is the average cost of hand-on bridge inspection for the elevated bridges, including traffic control?
That's a great question. So I don't have that number because all of the bridges are different. As you might guess, all the span configurations are different. Just the direct connectors and the traffic going into each one of those is different. But we are talking, if we have 480 spans every 2 years, and just to inspect all of those, is upwards of 2.3. And so that number is actually last year's number. I'm sure that each year it increases. So as you can imagine, it's very expensive. And if you think about it in terms of the life of the structure, so LRFD, under LRFD bridge design, we design them for 75 years. That's kind of the year. So every 2 years, it definitely adds up.
And Jamie, what happens if a bridge inspection doesn't get done on the 2-year time when it's supposed to be done?
Well, we definitely hope that doesn't happen. All of this is regulated by FHWA, the Federal Highway Administration. And so every year we have checks on this, and we actually go into, they're called PCAs, and that is kind of like we have to have a plan to correct it. And so everything is looked at very heavily, and that's for all the states. That's not just Texas.
Yes. And another question, and you might ask the audience for suggestions on this too. Is there any way to lessen the inspection cost while maintaining quality?
Well, that's a good question. So I'm assuming that they mean twin tubs, or is that just in general? I'm wondering.
I think it's in general.
I think just as, for fracture critical bridges and steel bridges, definitely need to think about that. And if there are other alternatives to what you're doing, especially if you're going over a railroad, there's a lot of issues with that. And there's a lot of coordination with the railroad and just things that we, someone asked before, if we don't make that 2 year in time, we have had to get exceptions just if we are going over railroads. Sometimes that does take longer. And so it may be delayed by a couple of more months to get that inspection. There's definitely things you can look at. I know for the steel box straddle caps, I sat down with an inspector one time, and we just talked about, the straddle caps, they want to be able to get in those to inspect them. And so anything you can do to make it easier for them, just as far as just the ability to get in there. And then also you think about drainage that might, or, if water gets in there, you need to make sure that you detail it for that.
All right, I don't see any more questions. So I want to again thank you, Jamie, for the very informative presentation, and